Okay, good afternoon, everyone. My name is Maddie Hornsby. I'm the project manager for the Riot organization. Welcome to the Riot Lunch and Learn series, the place where we spotlight Riot sponsors. Today we have with us GSI and AEM group to speak about real-time AI for Edge IoT. Just a couple quick reminders before we get started. This event is being recorded and will be posted to Riot's YouTube channel and uploaded to the meetup page where you registered for this event. If you have any questions throughout the presentation, just place them in the chat and we'll get to those at the end of the presentation. And then please keep yourself muted throughout the entire event. With all that being said, I will pass it over to Ed Bray with AEM Group. Welcome, Ed.
Thank you, Maddie. I appreciate it. I appreciate everybody showing up for this on this Wednesday afternoon. We're really excited about introducing GSI technology to the market. They're an innovation partner focused on high-speed computing at the edge, and I think you'll be if you're focused on AI or edge computing in the IoT ecosystem, you will be very enjoy this information, this presentation greatly. I'll introduce the GSI team. Sheldon Wiseman is on as a regional sales manager, Mark Wright, director of product marketing, and George Williams, director of data science. Mark and George will be going through the slides and going through the presentation, and we'll take questions at the end. And don't hold back, ask as technical questions as you want. And then if we need to take them offline, we definitely will set up follow-up calls and can have meetings, because this can get pretty involved. So, but welcome, thank you very much. And we'll make sure we've got contact information and make ourselves available to you. Enjoy. And with that, I'll turn it over to Mark. Are you going to start?
I'll start, yeah.
Okay.
Thank you, Ed. Hey, George, can we go to the next slide? So hello, everyone, and welcome. As Ed mentioned, I'm going to turn my own video off. There we go. Okay, so given this audience, I expect folks know about IoT, and we will touch a little bit on the the promise that IoT has, which is beginning to be delivered. But what we're going to get into is some of the progression that's happening with the devices and the systems that are already out there. And this really touches upon the greater use of AI right now, which is at the cloud, but the need to evolve, as we go to, pressures in applications that are coming out now. Next slide. So let's just do a quick recap of IoT, right? So the value proposition of using the Internet of Things with our things or our products is, the simple one is we get to monitor things, right? The second one is we gain data on the thing's behavior by monitoring it. You may notice I have not put the remote control portion of it, but in some cases that, definitely that's a benefit. That by itself is not IoT, that's just remote control. But of course, the ability to remotely gather and control, command and control something that may be, very geographically distanced from the controller. But there's also gaining insight we gain insight from the past performance of the operation of these things, and then we can use machine learning to gain knowledge of the operational life cycle of these products, right? So far, this is nothing new. This has been, technology that's been around for quite some time. But then what we're doing with IoT is attempting to gain some knowledge and some intelligence of the systems that are using these things, right? So these things and potentially things from other neighboring systems to gain some knowledge. And then the ultimate goal is really to change behavior, right? So if we can change behavior, then we can improve safety, we can improve convenience, potentially lower energy costs or lower operational costs of the device. So this is kind of the promise of IoT. Next slide. So this is the current state, right? If we have, and I'm showing an industrial IoT here, a front loader, and we've got some sensors on there picking up some data. We filter and shape. Part of that is to reduce the data that we send. We send that data up to to cloud storage, but we also do some local command and control back to that device. So we got the closed loop on the device. Up in the cloud storage, we have a digital twin of that device. And we've got two things happening there, right? We're monitoring, we're making decisions on what it should be doing next based on maybe some new data that's come in. But we also then take that amalgamated data and we can do some AI on it on the cloud to for training of new things that are found, or if we're going to go to a new site, new materials, or the like, that information can get loaded into the digital twin, which then comes back into this wider control loop. The other picture down on the bottom right is by having all of this, we can take actual data learning from other systems that are related or used, the same type of sensors that we're interested in, but maybe installed in slightly different equipment to also incorporate that data into our AI learning. Next slide. Okay, so one of the problems we have that I want to discuss and really concentrate on the drive in the change is a bottleneck when we are moving all of this data, right? So current processors use this von Neumann architecture where we have the data in one area and then we process it so in another area. So we're constantly moving this, right? And particularly in IoT, we've got sensor data that's coming in. We have to store it. We're storing it at some bulk memory area. And then on top of that, when we want to process it, we take it from the host that wants the answer to the coprocessor, which may still be a CPU that's running this. And then that CPU would, particularly when we're doing the AI, will have the acceleration. And again, we're going through memory. So there's a lot of memory transfers, a lot of IO transfers that are happening here. Next slide. And to point this out, this limitation I'm just talking about, that's right even in the data center in the cloud. But if you consider it, this happens all along the way, right? So as we're in the digital twin, as we're moving the data to the cloud, and even as we're gathering that data at the sensor and putting it to the local MCU, there is still this von Neumann bottleneck that's occurring. But the bigger problem, or a big problem, is that it's occurring at multiple levels as well. Next slide. So what are the new pressures? So, and this is part of the problem with the von Neumann is it slows us down, right? That's the primary problem. There's a large latency between the actual measurement of the input from the sensor to gaining some additional insight at the data center at the AI system. Okay, so some of the new things that we're looking to do as we field IoT out is identifying new conditions, right? So and those new conditions can be because of learning we've got, because of new behavior of the machinery from its constant use, or just a new application of the machinery. So we've got some new conditions that we've got to program in. We've got to train new data, right? So if those of you familiar with networking, when you have an address that you want to go to that you've never gone to before, the system doesn't know how to get there. So you do an ARP, and so basically you don't know, you learn it, and then once you've learned it, that's stored back into the system, so that the next time it comes up, you know the answer already. So the ability to train new environments similar to an ARP would be useful, right? Rather than bringing the whole system down, retraining it, and then sending that data to the edge. Adding new items without a complete local database retrain, right? Again, so that may be the environment, maybe new component that's added to the equipment, right? Or a new application, same equipment, same historic behavior, but a new application of it. We want to add a new constraint to it. And so what we're trying to get to here is having the intelligence of the cloud data that we've warehoused, that we've been doing all of this AI training on, but it takes time. We want to do that locally. If we can do that locally, then we can speed things up, right? We get a lot of this intelligence in real time. And that's, there's a drive to that. So as we get to automated cars, when we get to ADAS, but also when we're getting to driving some of these ADAS cars on a freeway, right? We can't tell what's several miles down. So there's a need to have IoT answers or intelligence locally. Okay, and another one which is coming up new, is the integration of blockchain with IoT, right? So there've been a number of projects on here. There's a couple projects coming up, and I'm just trying to think of some names like Demo for vehicle data tracking, mappers, various of these integrations of IoT with blockchain, either for incentivizing or for data trust reasons. But again, you need some processing on there. You have to some increased processing. If you can bring that to the edge, that really helps this direction. Next slide. Okay, so what's the solution? So we have this picture here, where we're going from the original picture where we were taking the data, we were putting it in the digital twin. If we can bring this digital twin, the capability of that digital twin down locally, right? So currently that digital twin resides in the cloud. We take the data that we're gathering, we do our machine learning to create a model. That model goes into the twin. And we could either try things out on the twin and have it occur at the edge, or we have things at the edge that's occurring in the twin, and we can see it and we can do analysis to see, okay, what should be the response. If we can move that to the edge, then this local loop here becomes a lot faster, right? And we gain some additional benefits. We can still do the massive modeling in the cloud, but then if we can move that trained model, that trained database down into the edge here, we're getting that intelligence being applied locally, rather than just a simple control loop here. We actually have an intelligence-driven control loop that's occurring here, and then anomalies can still be sent up to the cloud, where we have a massive data set, right? We have a data lake here. We can data warehouse. Do the AI on that, and again, reload on here. Or ideally, in fact, not even retrain and reload, but send in vectors for our new, the new environments where we want to use it in, without having to do a shutdown. Next slide. Okay, so at this point, I'm going to hand off to George, who's going to discuss use of associative computing, which will allow us to have that memory density locally, and also that intelligence capability. George?
Great. Can you hear me, Mark?
I can hear you.
Fantastic. Thanks for the intro and the great background on IoT and where our technology fits. We mentioned in the title von Neumann computing, and the computing that we do in our chip, we call associative computing. I'll talk about that difference in a second. But I think first let's sort of ask ourselves a fundamental question, which is, why do we need a new paradigm in computing? And Mark touched upon some of the reasons why, and I'll do a deep dive a little bit on why we think this is important. So, in short, microprocessor design has not changed significantly over the last 80 years. As we mentioned, the reigning hardware compute paradigm has been called the von Neumann compute paradigm. And as some of you know, in this microprocessor design, memory is both logically and physically separated on the hardware substrate. Compute components such as an ALU, it issues read instructions to a bit line oriented memory store. Data is retrieved, the data is computed at the ALU, and the results are stored back at the data store. And notice that the data is being marshaled across this data bus at the bottom. And that has ramifications, as Mark mentioned, in terms of compute latency and in terms of power consumption. So associative computing, what we do in our chip is quite different than the von Neumann paradigm. Here we enable bit lines. Those are the memory lines connecting memory cells vertically. We enable programmable bitwise computation that can occur directly on those bit lines. So in this compute paradigm, there's no transfer of data to a separate compute element outside the memory. And obviously in this paradigm, we can achieve tremendous savings, both in terms of compute latency and power consumption. All right. So, as I showed, we're performing these very simple Boolean operations on the memory cells on those bit lines. And we can do that on separate bit lines. So we can achieve a high degree of parallelism in this kind of compute. Now, we're talking about bits, we're talking about bit lines. The true computational power of this approach is achieved by scaling these computable bit lines within one chip. In our design, one bit processor can perform a bit line operation on 24 SRAM memory cells, but we scale 2 million of these bit processors in one chip across 4 quadrant-based cores, each core with 16 banks, each bank with 16 what we call sections, and each section contains 2,000 bit processors. So that's 2 million bit processors in a chip, computing directly on 48 million memory cells. Also not shown here, we have an L1 cache, 96 megabits of that, which is interleaved throughout the computable memory. So, in terms of applications, Mark mentioned a lot of the application use cases where we see an advantage, and we're exploring a whole lot more. I'll talk more about that. Natural language processing is an ideal application for this chip because we can take advantage of a lot of the advances in AI now with machine learning that can translate a word, a sentence, a document, right, into a feature, a compact feature vector. And then we can store those feature vectors directly on the bit lines in our chip. And this enables large scale, low latency, semantic search on really large language databases. And we'll talk a little bit more about the algorithm in a second that is used to achieve this. In terms of the product offering, switch gears here and just talk about, what this looks like, right? I talked about our chip, but the chip's on a board. We have a mini PCI board form factor, the Lita G that you see there on the left, and a full-size PCIe board there on the right, the Lita E. And these are our commercial boards. We're also working on more ruggedized boards in conjunction with the aerospace and defense community. And ruggedized boards means, we've tested it. We've sourced components that work in various kinds of harsh conditions, such as radiation and heat, harsh conditions that you're going to find not on the surface of the Earth, but as you push further out into space. And so we have active collaborations, as I mentioned, with various defense partners. And so we'll have more information on that in the near future. So, application use cases, computer vision is has been seeing a resurgence of late, much of it due to deep learning and AI. And we have found that our chip and our approach to computing is a good fit for many fundamental computer vision use cases, especially large scale ones that I'll show you in a second. Some things that we've been looking at currently, synthetic aperture radar back projection algorithm. A lot of satellites are now being deployed with SAR technology, and the benefits to SAR are just tremendous, right? It's instead of a passive optical imagery, SAR-based satellites can actually map areas when it's dark. It's an active radar technology, and it can deal with cloud cover as well. So we're seeing a tremendous amount of activity in this space, and we've started to look at various fundamental algorithms which take SAR data and then project that into something that is more visual. Other fundamental computer vision algorithms we can do very quickly and with low power consumption, histogram equalization, convolutional algorithms, some LiDAR processing types of use cases that we're looking into, especially related to LiDAR compression. LiDAR produces a tremendous amount of data, and so on-the-fly compression is very key for the LiDAR pipelines, as well as dense registration and simultaneous and SLAM-based pipelines as well. I'll get into some of those in a second here. And we're continuing to build up our corpus of computer vision algorithms. So I mentioned, the tremendous interest in SAR these days. A lot of SAR data that needs to be processed. And typically this is happening not just on board the satellites, but also at data centers. I mentioned the benefits of SAR, right? You can penetrate cloud cover and it can actually map regions that are not being lit by the sun. And we can map areas that traditionally have been off limits with respect to traditional satellite kinds of technology. Apologize, this is a dizzying slide. We do a lot of performance metrics with respect to our chip. I'll just guide your attention to here where we demonstrate our algorithmic performance, where we can support variable size fixed point, which is not easy to do in other compute architectures. We can demonstrate various kinds of power and performance improvements, not just in terms of performance of the algorithm, but also the size footprint within a data center. And we compare ourselves against the traditional players in this area, CPU and GPU. We're going to leave slides. Slides will be available after the talk, and so if you're a numbers person, you can pore over a lot of these benchmarks offline. Similarity search between two images, understanding how images are similar structurally is very important for large scale imagery, especially the ones you find in satellites. And that's tremendously important for these point cloud databases, which are really large. And we want to compress these data sets, but we want to compress them in a way that biases towards compressing structural similarity. And so we've done a lot of work in this area, accelerating this kind of HPC algorithm. And then I'm going to skip over this slide, which is related to that. Again, offline, if you're interested in our power performance improvement over traditional compute paradigms, this would be the one to focus on. And just quick results, right? This is it's hard to appreciate here because we're dealing with really large, high resolution images, the kinds you would find in satellites, and we can compute correlation heat maps on original images really fast with our chip. Dense registration, another very important algorithm in the aerospace and defense community. You're going to find these kinds of things in SLAM pipelines, where you sort of have sequences of frames, and you kind of want to understand, what is the mathematical operation which kind of takes you from one frame to another. And that's useful information if you're developing navigational systems that are based off of optical kinds of data. So doing this very fast, obviously, in these flight control systems is going to be key. And this is where our approach really shines, our in-memory parallel approach, programming each of those 2 million bit processors to process patches of these really large images. We do that really well. I'm going to skip this number slide here. You can consult that later if you're interested in our performance on dense registration. And we're doing acceleration on fairly basic computer vision algorithms. Large images, of course, right? You need to do this fast. You need to do this power efficient. And that's something that we can do on our chip. And we're increasing our CV algorithms really on a regular basis. And just some visual results on histogram equalization and convolution. This is better done with a live demo. And so if that's something you're interested in seeing, we can set up a demo offline as well. So, Mark talked about, right, we have all this data, right? We're trying to get insights from it. Computer vision, deep learning gives us some powerful capabilities to surface some of these insights. And a lot of these are semantic, right? Taking an image, taking a sequence of frames in surveillance streams, video streams, and trying to understand, not only what's in it, but the context of what's in it, right? Is this a threat? Is this not a threat? Situational awareness depends on accurate and precise, and in many cases, down to the pixel kinds of classification. And AI gives us the ability to do that, right? You see that on the right. You see the tremendous advances in object localization and per pixel classification on images. And this gives us a tremendous understanding of what a particular camera is actually seeing, and then to create a pipeline that not only recognizes these objects in surveillance streams, but potentially recognizes the same object in multiple surveillance streams. And so that kind of re-identification technology is important for situational awareness that goes beyond one camera and goes into a multiple camera kind of scenario. And this is important for, as I mentioned, situational awareness and security in lots of places that it's needed. Our approach, right, one based off of training lots of different kinds of AI models, right? You take your choice. You can actually customize this for the objects you might be interested in with respect to video and images. Localizing those, sometimes down to the pixel for each image in a video stream, multiple video streams. And then from that, we create ensembles. And from those ensembles, we create a context vector, a fingerprint, which identifies that scene. And that's important because we might want to actually, over a large period of time, understand if we've seen this particular suspicious object or suspicious person in the past. And by translating each frame into this context vector, we can store those efficiently in the bit lines of our chip, and we can search really fast, long periods of time in which to surface that kind of data. And then, obviously that this whole module can be plugged into some kind of notification system, and it can be automated. In terms of, those are algorithms. We also do a lot of work integrating into a lot of applications and frameworks and services that people know. Elasticsearch is very popular within various communities in e-commerce and aerospace and defense. And so we feature a plugin that if you have an existing Elasticsearch database, you do vector search already, you install our plugin and you can get the performance benefits of our chip for doing that kind of search. And we support very large scale databases. These databases are quite large, millions of records, many of them are getting into the billions. And we focused a lot on supporting large scale search on billion scale databases with millisecond search latency and high accuracy. More benchmarks with our Elasticsearch plugin. We compare against other implementations in the industry. Vespa, our plugin. Elasticsearch has their own search and vector search implementation, and our performance compared to other implementations is quite good in terms of both latency and in terms of both accuracy. And you tend to need both when you're doing large scale search. I'm going to skip this one. We do compare against a large number of data sets in this area of vector search. And change detection, we talked a little bit about, how do you surface insights when things are changing at the scene level, not just the pixel level. And AI is integral to this kind of approach. Change detection approach. ATR is kind of the acronym they use in the aerospace and defense community. But if you sort of take two images over time and do a pixel difference, right? That's not going to be very useful because you're gonna get a lot of the jitter that's naturally occurring when you capture those images. The capture technology isn't perfectly aligned. So you do need to go deeper into scene understanding. And that's where these approaches with AI and with our fast vector search, we can achieve much better performance. And here you see an example where we do take pixel differences, right? These are satellite images over an area that's taken over two large periods of time. And we get a better indication with respect to AI and change detection. What has really structurally changed from a scene perspective between these two different points in time where we've captured. Cybersecurity, this bitwise oriented architecture is ideal for a lot of these hashing algorithms, bitwise hashing algorithms. And we can perform these brute force decompositions of hash spaces very quickly in our chip. And this has various use cases, as you might imagine, just in general in cybersecurity, but also object deduplication, and of course in blockchain, as Mark mentioned earlier. And I would like to say that we do a lot of work with respect to AI. We contribute to various parts of the AI ecosystem in vector search and in deep learning. We are the proud winner of the Mafat Radar Challenge, which was trying to surface various kinds of insights, differentiating between various kinds of targets in a radar track. Right. In this case, it was different biological entities within a radar track. Tremendously hard problem. You're looking at the data set there. If you're familiar with radar data, that's not unusual to me. But trying to surface, right, trying to create and develop biometric footprint technology based on AI is a challenge. And there were over 1,000 contestants and participants to this challenge, and we took first place. This was in mid-2020. I'm going to round out by sort of talking about, our software stack is very mature at this point. It's a new chip, so we have to build a lot of custom microcode libraries, but On top of that, we built host level libraries for specific kinds of algorithms. I've mentioned a few here: search, digital signal processing, hashing. And from those libraries, we can develop other compositional algorithms, such as the ATR algorithm and the large scale search. And we've built various kinds of connectors and plugins into well-known applications. I mentioned Elasticsearch earlier. We actually plug into various face recognition pipelines and synthetic aperture radar platforms. And in biopharma, we've integrated into the BioVia pipeline pilot suite of applications. Now, a lot of this, the application libraries, the algorithms, and these low-level libraries, those are our primary interfaces for customers that need a particular kind of algorithm, particular kind of software support. For a lot of people, we might not have the algorithm, right, that they're targeted, or they need to take in-house the development of that algorithm. They can't sort of give us product specifications. We develop the algorithm, although we provide that capability. For a lot of, especially in government, aerospace, and defense, right, they want to create these things and keep it in-house. And so for those use cases, for engineers that want to port their own algorithm to our chip, data scientists that want to kick the tires on creating their own algorithms, we feature also a compiler stack. Our first compiler we are going to be releasing in pretty soon, actually February next month, and this will be our low-level compiler stack. But our plan is to have the mid-level and higher-level compilers also by the middle of this year. And I can talk a lot more about the software stack and all of the libraries we support, but I think this is a good slide that touches upon a lot of the areas that we've been working on, and we're continuing to work on more. Mark, did you want to mention anything about our software, our continually evolving and maturing software stack?
No, I think I'll actually save it for the next slide. Yeah. So on here, thank you, George. That was a good deep dive into what we're showing here. These are the products we've got. We've got the hardware we spoke a little bit about at the beginning. There is a new E1.L form factor, which is a much smaller. It's a 1U form factor. It also allows a lot of density in terms of processing because of the migration to server-based 1U SSD cards. We could use that same form factor and that same hardware boxes to hold these. There is the algorithm development. So there's a software component to this, as George mentioned, both at a high level where we have integrations in with product frameworks that are available, but we also have lower level compilers to be utilized with AI frameworks like TensorFlow and so on. And then on the right hand side, we also have systems. So where does all of this fit in, right? So as we were talking, we've got that edge speed up value proposition of IoT. So where does all of this fit in? So where the value proposition truly fits in is the ability to bring that AI processing that was done in the cloud down to the edge. So it's not extreme edge that may be in a camera, for instance, but it's edge being something like a desktop server that would be local in the use environment that that the operations are occurring in. So be that industrial IoT with heavy machinery, automated machinery, somewhat like Rio Tinto uses. On some of the examples that George talked about, we have two I'll bring up. One is, he mentioned the BioVia. BioVia is an interesting case because you can think of it as a digital twin in the cloud that's used to recognize and develop new drugs right, based on data that's already existent. And so that's almost like a cloud to edge rather than the other way around. And so we have an accelerator for that. In that situation, we are actually still operating in the cloud region. We're accelerating that. The second example, though, is more on, where I really wanted to talk to here, which was that edge. And the speed ups we can do, for instance, on the SAR examples that George gave, allow us to put a 1U box, as shown here, into an actual aircraft. So now, instead of an aircraft taking SAR data, radar data, storing that on a drive, getting back to base, and then running that for a couple of days to get the intelligence, you can actually get this intelligence in real time, right? And this is the paradigm shift that comes in IoT now. If you can do this intelligence at the edge, now, for instance, if there's a very specific example, if you're doing SAR on an airplane and you're getting the results there, you're finding smoke when you're looking for fires. You're finding land anomalies in things that you're searching. The pilot can get an alarm and swing back and do another sweep at a higher resolution, right? Whereas before it would be get back to base, analyze the data, and maybe send out another mission. So this is the type of paradigm shift that comes to IoT when you can bring this intelligence processing down to the edge. Next slide. This is our last slide, just showing some of the collaborators we're working with on this technology, to bring this capability to edge applications. And that's it. Thank you for listening, and we'll open it up for questions.
Wonderful. Great presentation, Mark and George. Thank you so much for your time.
Thank you.
Yeah, I unfortunately don't see any questions in the chat at this very moment, but everyone, please feel free to throw any questions that you might have in the chat. Or at this time, I invite you to unmute yourself and ask Mark and George a question directly.
This is Scott Gerard. I was wanted to find a little bit more information about the systems you have down there. You talked about the compilers. I'm sure that the low-level compilers are probably in some unique language, but do the higher levels get up to like Java or Python or some or C, some kind of language like that? And what does the environment on those systems look like? Is it a Linux system where we can install software? Just wanting to know more about that.
Yeah, so all of our software right now is based off of the Linux operating system. We're supporting Ubuntu right now, but the edit distance between supporting Ubuntu, at least for us, and other operating systems is pretty low. We'll probably expand that out based off of customer requirements. But yeah, all the host level software I showed you is Linux and Ubuntu. As far as the compiler, the first compiler, actually, the analogy I like to use with a lot of people, since I talk to typically data science and AI crowds, is AI compilers, which take an intermediate representation of a compute graph, and then produce from that compute graph optimized code for a particular platform, whether it's CPU or GPU or one of these other GPU clones that are out there. So some people call that a back-end compiler in that context. So in a similar vein, our first compiler is kind of a back-end compiler. The compute abstraction is not a compute graph, but what we call a bit level array. It's sort of an abstraction of the bit processor computing that I showed on one of the slides. And so from that sort of abstraction, our compiler takes that, which is defined actually in Python, where you defined your bit level array computation, and from that produces the optimized microcode. I can actually give an entirely different presentation on that technology. In fact, we have workshops where we're happy to invite anyone here interested in those workshops where we deep dive that on the compiler technology. But that's our first compiler. You have to know a little bit about the architecture, but the actual programming language is in Python. So it's embedded in Python. What you're talking about is a higher level compiler, which takes Python code and then translates that down to microcode and is transparent, right? What gets run on a CPU or what gets run on our chip. The higher level compilers are something that we're going to build on the low level compiler, and that's coming later this year. But the idea is first to support Python. Actually, the idea is first to support NumPy, right? If you're familiar with that mathematical library, we're going to be able to accelerate certain operations, many operations NumPy with our chip. But if your program already uses NumPy, like a lot of programs already do right now, it will be transparent, right? You're going to install, our NumPy support, much like what CUDA does with CUDA-Py, with CUDA-Py, and it'll be transparent, the mathematical acceleration you're gonna get, and so that'll be next, and then a higher level compiler, language compiler support such as Python. I'm big on Golang myself. We'll see which ones we decide, but Python will be the first language we support with the high level compiler.
But so if someone wanted to write a full-fledged application of which this APU is part of,
yeah,
they might start in Python and do the other pieces in Python, and then at some point call out to your processor.
Yeah. In that way, it's going to appear a lot like, we're just providing a shared library, and so you link out to that shared library. And then as we introduce the higher level compilers, it will be more transparent with respect to, or more, sorry, not transparent, more automatic with respect to, what part of the Python runtime we accelerate, and when we actually take over that computation and marshal it to the APU. Yep. Yeah. So, we're making it as straightforward as possible. Everyone, at least in my community with data science and AI, everyone's familiar with Python. And so even our first level compiler is geared towards you creating bit level array abstractions within a Python program. And yeah, so we're going to start to teach workshops in this in February. And, I think we're, at least I would love to extend invites to this community if you're interested in kicking the tires on our first compiler technology.
Thanks, George.
Yep.
Awesome. George, Mark, what's the best way for folks in the audience to get in touch with you all?
Not on mute. Okay. Yeah. There's two ways. We've got the folks on the call here. We've got Ed, Scott, and also Sheldon. So that's those folks are maybe more local to where people are. And then I think that's probably a good start. And then they can hand out our contact info as well.
That sounds great. I'm going to drop Ed's contact information in the chat for everyone so that they have that as reference. Speaking of the chat, we do have a question from Jasmine, and it says, can you speak on the pros/cons of using AWS IoT Core versus other IoT services, especially as it relates to ML and data analytics?
George, you want to, or I can address that as well.
No, I've been following at a service level a lot of the developments that the public cloud has been pursuing with respect to IoT. AWS, Azure has a pretty good stack as well. But in terms of comparisons, I haven't used it enough to give you any judgments or opinions here. But I know it's very trending, and there's a lot of technology out there for accomplishing this kind of application. Mark, if you you have some sort of observation.
Yeah,
of
not
what's
so much,
happening here.
not so much as a comparison, but certainly, it fits into, so where AWS, the IoT core and the IoT macros help you is, there's specific ones of the various infrastructure modules that AWS has. There's specific ones for IoT, but this fits into that model of if you're doing a larger scale IoT fielding, and you've got this data you want to ingest into the cloud, right? So it makes it easy to do that. They have, there's even the security plugins that will help with all of that. The actual edge portion, though, becomes something you're responsible for, the extreme edge, right? So the actual sensor, data ingestion, the data filtering, shaping, and then what you want to do in that command and control in that local spot, that's still completely under your control, under your responsibility. And then once you figured out what you want to lake, that's where you start taking these AWS, or Azure or GCS modules to take that data in. Right, and at that point you can start doing AI processing on those workloads. So that's kind of the two worlds that we were trying to show that separate. Now, if you're not so much to compare those different ones, but there is a comparison between that, and there are IoT platforms, if you will, which do take it all the way down to that edge, right? So if you are actually looking to build a system of IoT products, then you could look at a more integrated platform, something like an ALA Networks, and there's a number of those around as well. And what they do, in some cases, they pre-integrate with AWS. In other cases, they'll integrate with other clouds or private clouds, but they're giving more of that connection down to that edge. But still, this when I say connection down to that edge, I mean that entire device up to the cloud ingestion system. But what we're looking to do here is take that, which has become the standard, and move some of that high-end processing that's in the cloud, to be closer to the local, or not closer, but actually at the local processing environment.
Very cool. Very cool. Well, that's all the questions that I see in the chat at the moment. Thank you so very much, GSI team, AEM group, and everyone who joined us today. Definitely keep in touch and check out Riot's YouTube channel for a copy of this presentation. But I hope everyone has a great rest of their new year. Thank you all.
Very good. Thank you, Maddie. Thank you, everyone.
Yes.
Okay.
Have a great rest of your Wednesday, folks.
You too.
Bye-bye.